For this session, we have with us Devashish Shankar. He's the Principal Architect at Drishti, who's going to talk about the new developments in deep learning for unlikely industries. Devashish has been the part of founding team and has architected and developed a variety of systems, including the training pipeline, the data platform, the core action recognition model, and has 8 years of experience in data science and has a strong background in machine learning and deep learning. So let's welcome Devashish to MLDS 2022. Hi, Devashish. Welcome. Good afternoon. And also, I just want to quickly mention that we will have a quick 10-minute session on Q&A at the end of the presentation. So please drop in your questions on the Q&A tab. Devashish, welcome to MLDS, and the screen is all yours.
Thank you, Sajiti. 1 minute, I'll just try sharing my screen. So it's visible, the presentation?
Yes, Devashish, all good.
Yeah, thank you. So I'll be talking about the topic of manufacturing meets deep learning. So basically, how we have applied deep learning to the domain of manufacturing. Now, as you guys know, mostly these days, deep learning has led to a lot of advances in various areas, especially computer vision. And we have picked up one such important use case, which is automated analysis of factory floor videos. So in essence, what we do is you have cameras installed on assembly lines. We take that video, and on that video, we run things like object detection, action recognition, anomaly detection. And that data is sent to basically industrial engineers. We have a dashboard where industrial engineers, line operators, line managers can see that data, and they can better optimize the line. So this is like in the nutshell what we do, and I'll be talking about the technical details of how we do it. So this is a brief outline of the talk. First, I'll show a video which will introduce sort of Drishti in 3 minutes. So to give an idea of what, to give an idea of how, what the problem statement is. Then I'll demo the cycle detection and action detection neural networks that we have to give a taste of what the tech is capable of right now. And then I'll dive into the details of the neural networks that we use and the heuristics that we use on top of that. And then I'll talk a brief bit about the ML infrastructure that we use, because it's a very important part of a production deep learning system. And finally, we'll talk about some performance metrics and research areas that we're currently working on. So let me play a video which should explain in brief what, in 3 minutes, what Drishti does. So this is from our sales kind of website.
Every now and then.
The audio is, it's audible, right? The video that I'm playing?
Yes, Devashish, it's good.
Technology emerges that fundamentally alters the status quo. In manufacturing today, that technology is action recognition from Drishti. Traditional object recognition can tell you these are cars. That's because it identifies a single frame in 2D. Meanwhile, Drishti's AI can process multiple frames and includes a third dimension, time. Here you can see action recognition from Drishti, registering every step in this assembly cycle, which means Drishti can tell you that the line associate installed the hose, threaded the start bolt, secured the start bolt, and installed the fuel tube in that order, and with a measure of how long each individual step in the cycle took.
Drishti is making an impact on manufacturers in a completely unique way. The data set that is created from the machine vision and the AI we're applying to it is a set of data that no manufacturer has ever had before.
Customers are choosing to use Drishti in their manufacturing plants because manufacturing right now is very competitive. They're looking for differentiators that they can use to make their products more effectively and be able to do them with fewer defects. And with Drishti, we can provide that tool.
Manufacturers around the globe use action recognition from Drishti and the associated insights that come with new data to continuously improve manual assembly lines. With Drishti, manufacturers can address well-known manufacturing challenges like bottlenecks and line imbalances. They can minimize defect and scrap rates and identify and address training needs.
This is allowing them to find efficiencies and ways to optimize the line that they've never had access to. And we're actually excited about exploring with our customers ways to use this data beyond the obvious improvements in the line.
Whether manufacturers are seeking to boost productivity, minimize quality issues, drive standard work adherence, or generally improve assembly processes, Drishti can help. And that's just scratching the surface of what Drishti can help manufacturers do.
Drishti is being used today in manufacturing primarily in the automotive sector. We're rapidly moving, though, into other areas, including medical device, consumer products, electronics, virtually anything that represents humans at work where there's manual assembly occurring. We will be the leader in automated video analysis that allows you to create business insights from people at work. At the moment, we're focused exclusively on manufacturing, but as we progress, we're being asked to take a look at other environments, such as warehousing, retail, logistics, healthcare environments, food service. So the future is extremely bright.
So hopefully that gave an introduction of the product. Now let me walk over like a real demo of the product. So let me first, so the core problem that we're trying to solve is cycle detection and action detection. So first let me talk about what is cycle detection. So in assembly line, cycle is a unit of work. So you have a unit which is being worked upon that comes into the station, certain actions are performed on that unit, and then that unit leaves out. And this entire sequence is called a cycle. So the primary problem that we solve is cycle detection. And then of course we do action detection within those cycles. So let me play a video which shows you what manufacturing looks like when we have turned off Drishti. So you can see there is a unit which is a worker is working upon, and certain steps are being performed on that unit. But you don't see any data on this. And when the worker is done, so this black colored basically thing is the unit on which is being worked upon, and then the unit leaves. So this sort of ends the cycle. In a few seconds, you'll see the worker pulling in a new unit, which will start the new cycle. So yeah, so this starts the new cycle, and then this is a repetitive process which keeps on happening throughout the day. Now, let's see what happens when we have Drishti enabled. So here you can see our neural networks are detecting the unit, they're detecting a cycle. So you see the cycle ID over there. You see actions being performed, being detected and localized. And these actions are being attached to the cycle as the worker is working on them. And we also measure the time it took to complete the cycle. We also measure the time it took to complete each action. So this is basically the problem statement. We have another use case, which is anomaly detection. So I want to clarify this a bit. This is different from standard machine learning anomaly detection. What we do here is manufacturers are supposed to follow a specific sequence of steps called standardized work. So they're supposed to work in a specific sequence. And when they do not work in that sequence, sometimes it can lead to product defects or other issues. So anomaly detection is really standardized work anomaly detection, where we sort of find outliers in where steps were not performed in sequence. Let's say they were supposed to perform, if sometimes they do things out of sequence or miss a certain steps, it can lead to a defective product. So I'll just show a quick demo of that. So here, this black colored thing is the unit, which is coming into the field of view. You can see our neural networks tracking the unit and detecting actions, and the actions are getting attached to the cycle. And I'll just quickly move forward. So this is an example where the cycle was done correctly. So you can see all 4 actions were performed, and we said success, actions complete. But in the next unit that you'll see, the unit that is entering after that, the worker for some reason did not perform any action. And this you would see as is successfully sort of flagged as an error by the system. So this is like basically a toy example of anomaly detection, but we do like much more complex anomalies. So here you see the system flagged this is an error that the entire action sequence was missed. Okay, so let me talk about cycle detection. So basically, cycle detection can be simplified to unit detection. So as I said, unit comes in, cycle starts, unit goes out, cycle ends. And you can actually solve this using standard object detection kind of techniques. So you have a well-defined unit object, which is unit, sorry, well-defined object, which is the unit. As soon you define a work area in the screen where you say the work is supposed to happen, as soon as the unit comes in, you start the cycle. As soon as the unit goes out, you end the cycle. So this is kind of like neural network is still operating at a frame level. At each frame, it detects if the unit is present and where it is present. And then on top of that, you do heuristics or rule engines to define the cycle. So this is a simple example using an animation. So assume this square over here is the work area. And okay, not sure why the animation is not working. Yeah. So you see an object which is moving in. As soon as the object moves in, you start the cycle, and as the object moves out, it ends the cycle. Now, this is the most simple case of defining a cycle. It can be much more complex than that. Sometimes certain actions can start a cycle. Sometimes certain visual landmark changes can cause a cycle. So what we have done is we have built a configurable heuristics FSM. So it's a finite state machine that you use to define these heuristics. So you can configure it, and based on config changes, you can deploy this to new stations, and you can define a very custom rule engine for each station. And uh, our kind of innovation here was we have also built a semi-supervised model which can do object detection in using very few frames. So you don't need like a lot of data to train the object detector. So this is just one paradigm that we use. Now, why is this hard? So the reason this is hard is, which may not be very obvious at first, that there's a lot of variation on the factory floor. Units are of various sizes. They can be present at different locations, irregular trajectories, which makes tracking harder. Multiple units in field of view. There can be occlusion. There can be different variations in the hands and clothes of the operator, lighting changes, background variation. Just there's this immense amount of variation in the data, right? And this is the kind of reason why you need to use deep learning. So this is another real example where you have images from a video, and the unit in question is this blue color box that we are tracking. The neural network is tracking using that green bounding box. And you see in this, it looks kind of like a parallelogram-ish shape, right? And then the unit is kind of flipped, and it becomes a rectangular. It becomes a very thin rectangle in this image, and then it flips over again, and it again becomes a rhombus kind of shape. And then the unit is sort of occluded, by the hand of the operator, and the hand color is matching the unit's color, right? Which causes problems. And then you again have like the blue thing removed, and it has become a metallic color. So the color has completely changed. And now they have added like some PCB on top of that unit, right? So these are like the real life challenges that we face. And this is why we use deep learning. We train the neural network on different sorts of variations. And there's a lot of work that goes on sampling. And like basically we sample across various variations. We have automatic ways to sample data, mistake retrain data, and so on, to feed these edge cases into the neural network so that it eventually reaches the desired level of accuracy. So that was in brief about cycle detection. The next problem obviously is action detection. Now, action detection has all of the problems that I described previously about unit detection, plus it has a special problem. Now, let's say I have this mobile phone right now. Let's say I have a single frame. Can you tell whether I am placing this mobile phone down or I'm picking it up? You can't, because you need the motion. You need to know the direction of the motion. So single frame, we can't tell whether the operator is grabbing a screwdriver or he's replacing a screwdriver. So to do things like this, you need essentially multiple frames. So and plus there is enormous amount of variation in action detection. Operators can do it in different ways. Some person is left-handed, some person is right-handed, different various perspective variations. There are different ways of doing the same action. So there's just a crazy amount of variations in the data. So our approach has been to use the latest sort of 3D convolutional models. Like when we started, we were kind of the first people to use 3D Con, but now kind of I think it has become industry standard. So just let me give a brief demo of 3D Con. So in 2D Con, we have a 2D kernel which slides over an image. In 3D Con, you have a very similar concept, except you have multiple frames stacked together with each other. So it's like a spatiotemporal cube where you have, let's say 64 images I'll stack 64 images together, and that will form a spatiotemporal cube on top of which you slide a 3D kernel rather than a 2D kernel. And we use latest architectures in the Academia X3D, slow, fast, and so on. You can read these papers for more details. And our kind of innovation has been here that not the core architecture itself, but like we have adapted these architectures to do action localization rather than video classification, because most of these architectures were built for, you're given a video and you have to classify that video in n given categories. But what we are interested in, when does the action start, when does the action end? So what we are doing is action localization, which is different from video classification. So we adapted them to do action localization, and we have done a lot of work to make these semi supervised, so you need as little data as possible to this is an in progress thing to train these models. And now let me talk briefly about anomaly detection. So anomaly detection is something I talked about earlier, where workers are not doing in following standard work. So we need to detect that, right? And there's a tablet faced right in front of the operator. As the operator are performing the cycle, if a certain mistake or a certain thing happens, they're warned right there using a tablet, so that the defective product doesn't leave. And so this is the kind of way Drishti is augmenting human beings in some sense, because we are making the human beings more efficient. So now this is a very challenging problem, because human beings rarely make mistake. Like if a NN model gets to like a 95% NN precision, a data scientist will be very happy, right? Like 95% looks like a good number, but human beings are much more precise than that. Most human beings would have something like a 99.9% precision. So imagine you have 1,000 cycles. A human mistake will happen probably once in 1,000 cycles, whereas if you have a 95% NN precision model, it will make some 50 false alarms for one true alarm, which would really not be a good experience, right? On top of this, we have a latency requirement of less than 2 to 3 seconds, where you have to, otherwise the user experience is again pretty bad. So let me briefly talk about a few innovations we did to solve this. We have a FSM based validation engine. Like first problem that we faced was that defining these anomalies itself is complex. Like industrial engineers have very specific rules on when it's an anomaly, when it's not an anomaly, and operators follow all sorts of standardized work violations, and some of them are valid, some of them are invalid. So we first define a regex based validation engine, where you can configure certain regexes as anomalies, certain regexes as non-anomalies. And then, that is part one. Then how do you make the NNs more accurate, right? So this has been done using continuous mistake retraining. So we deploy a neural network, then all the errors that it makes are sent to human annotators. Human annotators correct that data. That data is fed back into the neural network, and this loop sort of happens a few times until you reach the desired level of accuracy. That was one important thing we needed to do, just because the amount of variation is so high. Then another thing that we have done is we have applied a technique from NLP, beam search. Folks from NLP would be familiar with this, but here it's slightly different. So I'll explain it in a bit more detail. Let's say you have a sequence, A1, A2, A3, A4. This is like the standard sequence that the manufacturer is supposed to follow. And your neural network, let's say, predicts these actions, A1, A2, A3, A4, with these confidences. So A1, it predicted very confident, 0.9. A2, it was slightly less confident. A3, it was very less confident. And A4, it was very confident. Now, if you have a normal argmax kind of based or a conf thresholding of 0.5, right, what you will predict is, and then predicted A1, A2, A4. And you'll say A3 was missed. And you'll raise an alarm saying, okay, action A3 did not happen. Whereas A3 happened at exactly the right position where it was supposed to happen in this sequence, and NN was sort of confident. So given the prior that operators make very few mistakes, maybe it makes sense to give the benefit of the doubt to the operator, right? And only raise an alarm when the NN is very confident that you have an anomaly. So we use beam search, and I mean this can be done using vanilla breadth search also. You basically split the actions into confident and non-confident, and then you try all possible combinations. You get all these combinations, because I'll try an option with an action, without an action, and then either you pick the one which is closest length to the standard sequence, or you have a language model where you basically do the log probability. So you take the sequence with the highest log probability on that language model, and that finally selects your final sequence, which is sent to the customer. So this has helped us so this essentially allows us to tune anomaly precision versus anomaly recall. Like if you configure this in a certain way, you can be very precise but you'll have low recall, or you can configure this to have high anomaly recall at the cost of anomaly precision. Okay, now one of the very important things here is to make a production deep learning application is the ML infrastructure. So just one minute, checking the time. Yeah, so there is continuous training and evaluation is a very important part of what we do. And I feel in fact that data matters more than models when it comes to deep learning. So, so we have our in-house infrastructure, which is called MLGym, because that is where our models train. And I'll explain briefly how that works. So you start with raw videos from factory floor. We sample randomly data from this, and that data is fed into MLGym in form of data sets. Then these data sets go to Drishti annotation service, which is the uh, internal service for data labeling. They label all the cycles and actions in that data. And then we have ML training workflow pipelines on top of Kubeflow. This is used for actually training the models. Training models is generally giant DAGs where some portion will essentially do a lot of data download, another portion will run one neural network. Sometimes you have like layers of neural networks. So the DAGs train the entire different neural networks, and then you have the inference. So once the trained model is deployed, you inference it, and this is the critical portion. So when we inference it, a portion of this data every day, a small fraction goes for human curation or human verification, and they correct wherever. Let's say we raised 50 errors, right? Those will or a sample of that will go for human curation. They will correct the mistakes, and those mistakes will feed back into the training data. And this helps us continuously maintain accuracy of our models across days. This is a simple overview of our ML ops stack. So we use GCP and NVIDIA GPUs. On top of that, we do container. So everything is Docker containers with Kubernetes, on top of which we have deployed the thing. We use Kubeflow, which is workflow pipelines on top of Kubernetes, which is used for training the models. On top of that, we have Drishti MLGym, where we have the annotation service, the continuous training, and the model store, where the models are stored. And on top of that, we have the monitoring service, where you have Redash and Grafana, where you can see all the metrics. We also have a CLI that is currently used for training the models. So and we also have annotation NNOps team, who sort of take the cookie cutter model training from ML engineers. So ML engineers only sort of focus on the complicated models, whereas cookie cutter models just go through this very cookie cutter training process. Now we're moving to this self-serve AI kind of mode, where you just go to create. So this is a in under development UI, where you can just go select your streams, label your data, create an annotation job, and train your models. So this is where we're trying to move to as we go more towards scale. Here are some brief metrics for the thing, where uh, these are across customers, what F-score precision recall so we have a daily monitoring job. Like you can see, December date is the x-axis. So every day we get monitoring numbers because of the human sampling that happens. We measure all the metrics. These are certain, in case of anomaly detection, we measure the true alarms, false alarms at a station level. And We also Toyota, I think, did some trials with our competitors where we detected 100% of all the anomalies. You can dive in deeper into a station level stats and you can see the number of errors, warnings. You can see the true errors, false errors, missed errors, and so on. Uh, I'll just briefly, I think I'm almost running out of time. So current research areas I'll talk about. So one thing that we're focusing very heavily on is semi-supervised learning. We have an in-house technique which is based on VAEs and GMMs, which has reduced the object detection like we can do using just 40 to 50 labels. And this is not some academic one-shot learning kind of paper, right? This is real models which are used in production at the accuracy levels that you saw in previous slide, right? So those we can do in 40 to 50 labels, which in terms of video labelings, it's actually very small. We have also done semi-supervised action detection, which has reduced the labeling data by 4 times. And we are actively working on more improvements in this area because we want to make it self-serve AI. We want to go towards few shot learning, and semi-supervised learning and few shot learning is really taking over the landscape right now. Another thing that we worked on is cycle detection without heuristics. So till now, a lot of effort was going in heuristics tuning of these models. So we have an NN architecture which entirely learns all the rules from data. So you just define a cycle. There is no rule engine, and it learns based on data. What you give a video, you get out a cycle. So that is something that has allowed us to scale very fast. And transformers for vision is something that we're exploring very heavily. So I think that is it. We are actively hiring. You can see more in Drishti careers page and for various roles. And if you have any questions, we can take that. So I can.
Okay, thanks Devashish. Very interesting session, and we do have a few questions on the Q&A tab if you want to take them up.
Yeah, 1 minute. I'm just trying to open that. Yeah. Being a fast moving assembly line, how exactly do you raise an alarm and how is that attended to? So the alarm is raised in a tablet in front of an operator, and it is like up to the operator. He can just ignore it also. Like generally we do some sound also on the operator, and they can actually reject that alarm, or you can say it's a true alarm. That is the implementation of it. I hope that answers. Along with the sequence, will any mistake be detected by Drishti? Example, a component placed on the wrong side of board. Currently, not, but in certain cases, we do some sort of different anomaly detections, but we don't do essentially defect identification. But yeah, in certain cases, we have done that also, like where you can see, like certain customers had a requirement, okay, this unit should be picked up using 2 hands rather than 1 hand. So we did a complicated mistake. Like these are customized efforts that we put from time to time if a customer comes with those requirements. What kind of models have you used to do this in real time, and how are the labeling done? So labeling is our in-house labeling tool. Real time also we run the 3D convolutional or whatever latest models are there, and we have our in-house built inference pipeline which takes in this data, and we have done some latency optimizations on the 3D convolution, like to be able to meet that 2 to 3 second kind of deadline uh, for raising the alerts into the mentor. The cost of justified versus is more than then how's the cost of so it's really, this is a good question. If human accuracy is 99.9%, which is more than the NN accuracy 95% tops, I won't say. I mean, I think we have, that was just an initial without the other innovations that I was saying, right? Then how is the cost of installing the action detection system justified versus the result of avoiding that 0.01% of errors? So it's more about, there are certain manufacturers which focus a lot on quality. So it's not just about that 0.1% of the product that went bad, right? It's about the customer loss that will happen. Like Toyota says its feature is that we will have 0 defects, right? That is the kind of mentality that they go with, that there should be no defects, and they take that very, very seriously. So reducing something from say 10 ppm defect rate to 7 ppm defect rate is considered huge in manufacturing. Like you've reduced 10 parts per million defect to 7 parts per million, right? That is considered like an amazing achievement across this. So they're measuring things at a parts per million kind of rate, and it is considered like a big deal to change these metrics. For anomaly detection, has the model created for one customer? In case you need to provide anomaly detection service to multiple customers for some domain, what is your approach? Do you train different models for different customers and deploy each model to customer specific tenant? Yes, that is the case. We do customizations because generic models, there are such specific actions that you have to detect that we can't have generic models so far, but we have made the training process cookie cutter and easier. So that is how we're approaching it. You can do one-click training. You can do training very easily. So that is kind of our approach to scale, and we're trying to move towards a self-serve AI, where either a services team or some customers actually have their in-house data science team also who want to try out these self-serve AI tools. Or you have one global. No, we don't have one global. Like in certain cases, we have like head detection, person detection, we have global models, but not for action detection. And what part of model is taken care by VA? Which no, it's a completely in-house. Like I did not want to go into complete details of it. Like we have our in-house. We don't have time for that. So it's the back propagation essentially happens through GMM. It's a technique that we have developed in-house. So the GMM is trained as part of the deep network training, and the unsupervised data is essentially clustered as a GMM, and you take the nearest neighbor with the cluster centroid to kind of get the action, the label for the object. How much resistance from factory floor workers, and what is your how much is the resistance from factory floor workers, and what do you do on explainable AI? For example, worker might deny anomaly, but model predicts anomaly. So we are actually, these things were always done, to be honest. Like these were done by people going on the factory floor, industrial engineers. They go with a stopwatch, they measure everything using Excel sheets. We have just automated that. So this has been being done since 1920, 1930 in the manufacturing domain. Like it's a science in itself, industrial engineering. How do you optimize lines, right? And we are coming as an assist to the operator. Like, it's not like we don't do any facial recognition. We don't do any operator recognition. It's all about the process. So this action is taking longer. If we move this action from station A to station B, your line will be 20% faster. That is the kind of analytics we're looking at. We're not looking at it, okay, this operator is doing work slowly versus this operator is doing work fast. Or there's no such penalty. There's no object recognition. There's no person identification as such. Yeah, I think that, yeah, I think I've answered most of the questions.
Yes. We have 2 more minutes to the next session. So if any of the attendees have more questions for Devashish, please drop it at our Q&A tab. And Devashish will also be available at the lounge section, I guess. Right, Devashish?
Yeah.
To answer a few more questions. But thank you so much, Devashish. It has been an interesting session. The demos are quite enticing. So thank you once again for doing this for us on MLDS.
Yeah, thank you.
Okay, thank you. Thank you so much.